Okay, it's recording. Okay, so just to revise sort of what we were discussing last lecture, we discussed this elliptic curve discrete logarithm problem. What is it? And we discussed some sort of attacks on it. And one category of attacks is called isomorphism attacks. Is basically to solve the discrete logarithm problem in another cyclic group of same order. And that sort of uses, like as a mathematical tool, it uses while pairing on elliptic curves. So I thought for today it would be good to discuss while pairing, to define the map and discuss some of its properties. And while I was preparing the lecture, I realized this is a good content for one lecture. So we'll discuss while pairing today, and it's also a good opportunity to revise on divisors that we discussed uh, 2 weeks ago. And then in next lecture, sort of we can continue and see this in more explicit fashion, to see how these attacks are there and what are these functions explicitly and some applications to cryptography. So for today, let's just so our goal is to define while pairing and discuss some of its properties. So this will use a bit of divisors. So let me start with recalling divisors. It's not described in the book. So a good reference for this is, so this is discussed in detail in Silverman's book on arithmetic of elliptic curves. So I'll just type it in the chat before I start. So second edition, and this is discussed in chapter 3. Most of the material is there. So that's a good reference. And otherwise, there are plenty of notes available online. But like, I would really recommend sticking to this book, because the thing is, from different book to different notations change, and then anyway, this is quite a involved construction and it's a bit notation heavy. So it's good to stick to one reference just to understand it for the first time, and then one can use different books to just see like slightly different variations of this, but it's more or less the same thing. So let's start with a revision of our divisors. So this is a bit of recall. So if we have a curve, let's say defined over a field K, then divisor is a formal sum that looks like summation np times p, where p is a point on curve, and this is a finite sum, right? So I can conveniently write this that p varies on all the points on curves, but this is like a finite sum. So for all but finitely many p's, np will actually be 0. And we also saw that if we have a principal divisor, which are basically divisors of the form so divisor of f, where f is a function on this. So what it means is I collect all the zeros and poles of it, and my coefficients are order of zeros and order of poles, where zeros will have positive coefficient and poles will have negative coefficient. So if I have a divisor like this, so set of all principal divisors is contained in set of all zero divisors. This is
Um,
because, yeah.
sorry, I'm sorry. I don't remember where the zeros and poles are coming from.
So we
Um,
start with a function. So f is a rational function defined on C, and
Uh-huh.
zeros and poles are basically poles of that f.
Oh, okay.
Let me say for some f in K of C. So basically, so a general divisor is just a formal sum, right? So you
Yeah.
collect a bunch of points, assign coefficients to it, whatever you wish. So that's a divisor, right? Inside
Yeah.
inside the set of all divisors, we have this subset set of all principal divisors where the motivation comes from function. So I start with a function and I associate a divisor to it. And what's the divisor? So I take zeros and poles of my f, and the coefficients are basically order of zeros and order of poles.
Okay.
So that's, yeah,
And
So it'd be
order of zeros are positive, and order of poles are negative.
right, right.
Yeah.
so it'd be going from the ring of formal power series or formal rational functions to rational functions over the complex numbers.
Or you can, if you like, you can take k bar, if that's, yeah. Like if we start with a number field, we can take its algebraic closure instead of working in C. So,
Ah,
yeah.
thank you.
Right. So, so what is nice is, so if we collect, so if we take a function on a compact surface, or yeah, on a compact, so we can think of this curve as a compact Riemann surface, and if we take a function on that, then the zeros of order, order of zeros and order of poles are exactly equal. So the positives will cancel out with all the negatives. And if we take degree of that divisor, that will turn out to be 0. And remember, if degree is basically sum of all its coefficients.
So this theorem that you stated, is this something obvious, or is this some
It's
that?
not obvious, it's quite a deep result.
Oh,
But
okay, okay, okay. All
it's
right.
no, it's not obvious at all. It's quite a deep result.
Ah,
So like like a very non-trivial thing obviously is to identify it with a compact Riemann surface and then to show this thing. So
okay,
yeah, I don't want to prove that.
okay,
But yeah, it's not, no, it's not obvious.
okay. I was wondering about the last, yeah,
Yeah.
last lecture. I thought I was missing something. Okay.
So yeah, so set of all principal devices is contained in set of all zero devices. But these need not be equal. If I take any random divisor that turns out to be degree 0, so let me say degree 0, just clarify what I'm saying. Then there is no reason that it should come from a function or it should come from uh, yeah, zeros and poles of a function. So let me define this. And these are set, obviously, these are contained in, so everything is contained in set of all divisors. Now, if I take set of all divisors, it's an abelian group because I can add divisors just by adding their coefficients, and it's also abelian. So these two sets, degree 0 divisors and then principal divisors, they are not just subsets, they will also form subgroups. Right? So what I can do is, and it's abelian, right? So like I can talk about quotient groups. So let's say, so from a general curve, I'm changing my setting to elliptic curve. So let E be an elliptic curve defined over a field K, not necessarily a number field, it can be a finite field as well. So this object, let me define this, divisor 0 of E, or let me stick to the notation or the terminology that book uses. It's called Picard zero. So this thing is basically quotient of group of all degree zero divisors on E mod out by group of all principal divisors. Now what I'm going to state next, it's quite amazing and it's quite non-obvious. But again, because I want to focus on while pairing for today, I'm not going to prove this. But this amazing result, it's that if we start with an elliptic curve and we sort of take this object, this quotient group, Picard zero of E, then this is actually isomorphic to my curve itself. And this is not true for higher genus curves. So elliptic curves are genus 1, but if we go to higher genus, let's say genus 2 and beyond, this thing is not true. So my Picard zero doesn't give me my curve. Instead, my curve sits inside this big thing. But they are not isomorphic. They are not same. But for elliptic curves, it turns out that magically they are same. And this
Wow.
isomorphism, yeah, this is quite amazing. So elliptic curves are quite an exception in that sense because genus 2 and beyond, these curves behave rather. So elliptic curves behave differently than the other genus curves. So this is the isomorphism. So let's say I have so what is Picard zero? It's a quotient group, right? So let me take an element in here. So let's say a divisor here, which is actually a class. Then this will be similar to a point minus zero, and this zero is the identity point, or rather the point at infinity, which serves as the identity of the group. So let me just say point at infinity. Point at infinity. So if I start with a D, there I can find the pieces that this is true, right? And this map is basically send D to this point P. So let me say, so there exists P such that D is equivalent to this divisor. So this is my map. And let me give this map a name. Let me call it sigma. So when I say sigma of D is equal to P, that's exactly what I mean. I start with a degree zero divisor. I find a point P such that there exists a point P, so that's equal to, and sigma sends basically that. Okay, so now using this, what I want to, so this is an observation, and we will use later a lot. So this is good. It's good to state it. So D is principal if and only if the following is true. So let's say I have so D is a principal divisor. So D looks like summation NPP, where summation NP. So summation NP is 0, right? That's the definition. But what is nice for elliptic curves is that to verify if a degree 0 divisor is principal, if and only if so I add the points in my elliptic curve. So summation NPP is actually the identity. So this addition is taking place in elliptic curves. And yeah, let me say D degree 0. Just to clarify what the other notation means is my D is given by sigma and PP, right? So I pick the coefficients, I pick the points, and then I add the points in elliptic curves. So if my divisor looks like, let's say, for example, 2P minus 2O, this is a formal sum, right? But if I want to verify if this divisor is principal or not, here is what I do. So I take my point P, I add it to itself twice. So I literally do P plus P, but this is now in elliptic curves in E, okay? And then I do O plus O, but O plus O is simply O, so minus O. And then if P plus P turns out to be identity, then my divisor is principal. Or in other words, this is principal if and only if P is a two torsion point. So this is what I mean by this notation, just to clarify. So let me delete it. And let's see why this is true. Because it's helpful to see the proof, just to get used to this. So suppose D is principal and D is degree 0. So this is if and only if. So D is principal, right? So every principal divisor, basically those are the identities. So if and only if D is equivalent to 0. But if D is equivalent to 0, that means this map sigma, I'm sending it to the identity point. Now let me plug in the value. So let me assume that D is sigma NPP, just to sort of complete. So now let me just plug this thing here. So sigma of summation NP P is my identity. And now let me manipulate this equation. So to this, I can always add 0. Adding zeros don't affect my divisors, right? So like if I have something like P plus Q, then I can always do P plus Q minus 0 times another point. That I can always do. So sigma NPP, to this I subtract the following. I take the coefficient. So I'll attach my coefficient to identity, right? And here is the coefficient that I choose, sigma NP. Now this won't affect anything because we started with a degree 0 divisor, right? So sigma NP is actually 0. So I'm actually subtracting 0, right, to this. But this will help me rewrite my divisor in a nice way. So I can rewrite my divisor as sigma NP P minus O. Now this sigma, it behaves nicely with summation on integers. So this is actually sigma NP sigma of P minus O divisor. This turns out to be identity. But now, where does sigma of P minus O go? It's basically just P, right? So this is if and only if sigma NP P is 0. And now we are back in elliptic curve. So this is elliptic curve addition. Okay. So, and again, this won't work for high-genus curves simply because we don't have this nice thing that if I quotient out my degree 0 divisors with principal divisors, I recover my elliptic curve. So I'm using that isomorphism here. Anyway, so now if I start with a degree 0 divisor, and if I want to verify whether it comes from a function or not, I literally have to add points in elliptic curves and see if it gives me identity. And then I know it's a principal divisor. So with this observation, let's try to define our while pairing. And it's slightly involved construction, so I'll do it slowly and just go step by step. So again, just to set things again. So this is my setup. So E is an elliptic curve over K. Just shorthand. So what I mean is it's an elliptic curve defined over K. So what I mean is elliptic curve is always given by an equation, right? A polynomial equation, y square equal to a cubic in x. So the coefficients come from K. That's what I mean. And let's choose n, which is a natural number, but not just any n. I want my n to be co-prime to characteristic of K. So what I mean is, so there are only two possibilities for characteristic of a field. It's either 0 or it's a prime. If it is prime, I don't want P to divide n. And if it is 0, then it's okay. Any n would work. And this En, this notation basically means, oh, it's okay, Dimitri. Yeah. So En, this notation basically means that I'm collecting all the points in my, let's say I go far up, okay? I go to the largest possible extension, K bar. So what is nice about K bar is if I start with any equation in K, I know I can always find solutions in K bar, right? So for characteristic 0, C is the ultimate thing. But the closure is like complex numbers is too big a field. Like if you start with Q, all you have to do is to solve any equation, polynomial equation, just go to Q bar and that will work. Q bar is smaller than C, or like anything works in C, but we can work with smaller things. Anyway, so if I start with any field, all I have to do is to go to K bar to collect all the points. So I take all the points such that when I add P to itself n number of times, I get identity. Okay. This has a name. It's also called the set of n torsion points. The word torsion comes from like group theory, like they have a finite order of n. And anyway, so this is what I mean. And now this while pairing is basically a function from, let's give it a name, En. So it takes a pair of n torsion points and spits out an nth root of unity. So let's see how the magic happens. How can we get a root of unity from two torsion points? So here's the recipe. So let me start with any torsion point. Let me give it a name. Let me say it's Q. Okay. And let me look at this divisor. So what I do is I take n times Q minus n times O, where O is the identity, the point at infinity. Okay. Now this is a degree 0 divisor, but is it a principal divisor? So to check if it's a principal divisor, I use the observation that we just discussed a few minutes ago. I literally add the points and see if they give me identity. Q is pair of integers, C is pair of real. That's correct, George. Yeah, that's correct. But yeah, what I was saying was that C is actually too big a field. If all we care about is solving polynomial equation, then we just have to go to Q bar and not C. Oh, this was a response to another question. Sorry, I didn't see. Q bar is countable, C is uncountable.
Yeah, that was my comment of just how much bigger C is.
That's correct. Yeah, it's huge actually. I mean, it contains elements like E, like Euler's constant and pi that will not show up as roots of any polynomial equation. So it contains a lot of other numbers. Anyway, so back to this. So yeah, so this is a degree 0 divisor. To check if it is actually a principal divisor, what I do is I literally add the points using coefficients and verify whether it's true or not. So what I'll do, I'll add Q to itself n number of times, but that is identity, right? Because it is n torsion. And then adding identity to itself will only give me identity, right? So this is actually a principal divisor. So I can find a function f such that this is equal to divisor of f. So let me write. So nq minus no is principal. Hence there exists a function f such that it is divisor of that. Let me not, there's not theta, this was supposed to be O, so let me write, I meant O. Yeah. Anyway. Yeah, I'm not telling you what this function is, and I have not constructed this function. We'll do this in later lectures, but not now. All we care is that there is some function. Okay. So that's our f. Okay, nice. So now let me do another thing. So let me choose a point, or let q bar be any point rather, such that, so this is true. So when I add q bar to itself n number of times, and this is capital N, I'm sorry, I recover q. And I can always do this. There is no guarantee that the q bar will be, there is no guarantee that these n torsion points are defined over base field anyway, right? They will lie in some higher extension. So in k bar, I can always find a point such that this is true. So let me construct another divisor. So this divisor is follows. So q bar is this point, right? Such that n times q bar is equal to q. So using q bar, we will construct another divisor. And the divisor is as follows. So I take this point q bar plus r, attach coefficient 1 to it, and then I take this point r and attach coefficient -1 to it. This is my divisor. And where is r? So r is varying over all the n torsion points. Okay, this is my divisor. And now this is a degree 0 divisor, right? Because for each r, what is the sum of coefficients? 0. So if you add it for each r, all the coefficients will add up to 0. So this is a degree 0 divisor. But is it a principal divisor? So for that, what we need to do is we literally need to add all the points to see what we get. Okay. So what will happen if I keep adding all the points to itself? So I'll get, so let's say, so first of all, what is the, because I'll be adding q prime to itself. How many points are there in this, right? So we need to know how many points are there. So there are actually n square points that are n torsion. Okay. And one way to see this is it's not immediately obvious that when I collect all the n torsion points, I get precisely n square points. Like at least from the approach that we have seen elliptic curves in form of an equation that we get using Riemann rock. But yeah, using that, it's not fairly obvious. So if you so there is another way to think of elliptic curves. One can think of elliptic curves as points in lattice in the complex plane. So when you think of them as lattices, basically all the points that will turn out to be n torsion are of the form Z mod n cross Z mod n. So as a group, it's isomorphic to this thing, Z mod n cross Z mod n. And this set has cardinality n square. So this is
This is because you can cut your torus open into a rectangle, and that lets
exactly,
you.
exactly, yes. So yeah. So
And
to
that I think that is why this won't work with higher genus.
that's correct. Yep, that's correct. So this set has cardinality n square. So when I'm adding the points to itself, what I'll end up doing is I'll end up adding q bar to itself n square number of times. And then r and minus r will cancel out with each other. So all I'll be left with is this. But remember how we defined q bar. So n times q bar is q. So this is basically n times q bar, which is n times q. But q was n torsion, right? So this is just 0. So this is also a principal divisor. So there exists a function g such that divisor of g is equal to this thing. Okay, so we have got all our ingredients. We have got f, we have got g, and now we'll define pairing using these two things. So but before we do that, we need to, so here are some more observations. So if I raise a function to a power and I want to ask what is its divisor, then so if I multiply two functions, what happened to the zeros? So order of zeros basically get added up if I'm taking product of the function, right? So order of zeros will be added up, and similarly order of poles will also get added up. So divisor of product is sum of divisors. So when I take product n number of times, I'll be adding divisor n number of times.
And this will still work if the zeros or poles have multiplicity.
Sure, yeah, this would work because I'm multiplying function with itself, right? The
Yeah.
multiplicities would also add up.
Thank you.
Yeah. So n times divisor of g, and what is this? This is simply n times. So n times this big sum. So but I can pull n inside basically. So this will turn out to be summation r in en n q bar plus r minus n r. Okay. So this is my divisor. But let me look at another function. Let me look at f composed with the function that I'll represent by this sort of square brackets. And what is this function? So let me define this function first before I talk about composition. So on my elliptic curve, I can define a function like this. So what does it do? It's quite intuitive notation. So I take p, I send it to n times p. Any point, I just send it to n times itself. That's what this function is. So all the n torsions will go to 0, basically. So the kernel, or like sort of the pre-image or the fiber set of identity, consists of all the torsion points. This is my this is n. So suppose I compose this with f, and remember f was the function that we defined in the beginning. So I started with the torsion point, and f is this divisor such that this. Oh, by the way, this is small n is capital N. Sorry. Yeah. There is only one n throughout, so yeah. This should also be capital. So what is divisor of this composition? So let's just analyze this. Okay, so how does composition work? So f of n of any x, it will be f of nx, right? So what happens to zeros and poles? So what are the zeros and poles of f? So divisor of f was this. It was n times q minus n times identity, right? So there is a zero at q of order n, right? So what will happen with this composition? Basically, if f of n of x is 0, I want n of x to be equal to q, right? So I want all those points such that whenever I add n to them, I get q. But I already have one such point, q bar. And then if I add any torsion point to itself, that will suffice, right? So n times this will be n times q bar plus n times r. N times r is just 0 and n times q bar is q. Okay. So these are all the zeros essentially. And similarly with poles, same thing would happen. So if I take this composition, then its divisor would turn out to be, so all the zeros, and now again the order we have to remember. So the zeros are now q bar plus r. Basically r is varying in en minus r. This is just takes a couple of minutes to get used to whenever one sees it for the first time. So all I'm saying is, like, I've taken this composition, right? And if you just observe where the zeros are going to be, so f had only one zero at q of order n, right? So the basically, if I want this composition to have zeros, I want all the solutions to q over n. I already constructed one, and all the other are essentially given by just adding torsion points. Okay. And similarly, same thing would happen with poles. So I'm just adding r to 0, so I'll get r. That's. But now just look at this divisor. This looks familiar. This is basically same as the divisor that we constructed here for g to the power n. Okay. So this composition and g to the power n have same divisor. Now what does it mean? That they have exactly the same poles, exactly the same zeros, counted with multiplicities. So at best, they are constant multiples of each other, right? They can only differ by a constant multiple. So instead of, so what this means is, this is equal to g to the power n up to a constant. But it's only a matter of a constant, so I can always assume that I can always assume that the f that I chose in the beginning, I can adjust it by a constant. So remember, there was a choice, right? So we chose our f. Again, this is an, let me sorry, just so that when you're reading notes again, there should be no confusion. So it's always the same. And yeah, so I can always adjust my function by a constant. So assume that I have done that. And now, so by adjusting f with this constant, assume that these things are actually equal. So f of n is actually equal to g to the power. And this, like, there is something hidden here, right? So I started with a point q, and everything that I've done after that involved that q, right? So let me also add this notation just to sort of keep track of that q, because there was a choice involved. If you start with a different q, then these functions might differ, right? So again, we are almost there. So suppose, so I want to define a pairing, right? And you can already see there is a power n appearing. So we are heading towards roots of unity. But so far we only used one point. We need to use the other point. It's a pairing, right? So here comes the other point. So let P be another n torsion points. Then for any point x in E, if I take g of x plus p to the power n, where g is this function constructed, this is basically fq of n. So g to the power n is basically fq composed with n. So applied at x plus p. So this is the, and now what is fq of n at x plus p? So fq composed, so this n will act first. So this is simply nx plus np. But p is torsion, right? So np just vanishes. So this is fq of nx, but this is fq composed with this function at x. But what was this? This was basically my gq, right? Fq composed with n is gq to the power n, right? And now this equality, it gives me my root of unity that I want. So this gq at x plus p divided by gq at x to the power n is 1. Okay. So this implies that this number is some nth root of unity. Now there is a subtle catch here. The catch is that there is a choice of x involved here, right? I mean, for all I know that you choose a different x, this equality would still hold, but you may land upon a different root of unity, right? There is no reason why, like, if you keep varying as it varies in x, why that root of unity must stay constant. But this turns out to be not the case. So this not implies, I mean, this is, so this does not depend on x. And I'm saying it's not trivial. It's not trivial. The fact is, like, this, so what I'm doing here, so you can think of this as a giving a function from E to P1. So I start with x and I send it to this thing, gq of x plus p over gq of x, whatever this thing. But, like, we are using some properties of schemes and everything here. So, like, for example, E is smooth and everything. So this thing turns out to be rather a morphism of schemes. And it's so every morphism is either constant or it's surjective. But it cannot be surjective because P1 is infinite, right? And this only takes finitely many values. There are finitely many roots of unity. So it cannot be surjective, so it's constant. So when this construction, you think of it as function of x, it doesn't vary with x, so it's really constant. So this choice does not depend on x, and which is nice. It will prove to be very useful later on. And also, otherwise, this construction wouldn't really, yeah, it has to make some sense. So I'm all done. So this is my while pairing. So En, so you take a pair En, and so if I start with P comma Q, here is what I send it to. I'll send it to GQ of X plus P over GQ of X, where X is any choice. You can choose any X of your choice, and this will work. So okay. But what good is a map if it doesn't satisfy nice properties, right? This was quite so. In next class, we'll see how we can explicitly construct these things, these G, Q, and F, and everything. It basically boils down to doing addition on elliptic curves. So one can choose nice. So basically, it's all about choosing poles and zeros, right? So we'll see how we can cleverly choose that. So we'll make these things more explicit in next lecture. But this is a pairing. So whenever you see this word pairing, right, it means that it satisfies some nice properties. So here are some properties of while pairing. So first of all, it is bilinear in both variables. What this means is that if you fix one and suppose you want to add first variable, then this is doing one at a time and then multiplying them. And by the way, this concept is not like it's not like this word was invented just for this pairing. Bilinear is a more general concept. It can be generalized. So basically, what we did here. So En is a group, right? If you take set of all n torsion points, it forms a group because you add any two n torsion points, you add it n number of times, they will also go to zero, and it contains inverses and identity and everything. So I'm taking product of two groups and I'm defining a map from product of two groups to another group, right? So these things can be generalized. I mean, all the bilinear and everything, this can be generalized. What is nice with elliptic curves is it gives us so many like explicit equations and has specific applications in cryptography. But as far as this word pairing goes, it's a more general concept. So like so if you add two variables, it's like composing one variable at a time in the group, right? Here we have roots of unity, so our operation is multiplication. That's why you see multiplication here. If your codomain was an additive group, or if the operation was addition, we would be adding here instead of multiplying. So that sort of a thing. And this works in both variables. So if you fix p and we add q1 plus q2, this is same as doing en of p comma q1 and then multiplying it with p comma q2. Okay. This thing is alternating. So alternating essentially means that when you switch the variables, sign changes. But here sign changes would mean it's a multiplicative group, right? So sign change would basically mean that we are taking inverses, so multiplicative inverses. So En of p comma p is 1. And this actually implies that if we switch, they're not really equal, they are inverses of each other. Okay, this is what alternating means. Third property is that it's non-degenerate. What that means is that if En of p comma q equal to 1 for all q in En. So let's say I'm fixing a p and I'm varying this q over all the n torsion points. And if it turns out that for every q I am getting 1, then my p must be identity. And similarly for other variable. Uh, so if, because they are inverses, right? Like proving one suffices to prove other. So if en p comma q equal to 1 for all p in en. So if I'm fixing q and I'm varying p and I'm observing 1, then that simply means that my q must be identity that I started. So this is non-degenerate. Fourth property is that it's Galva invariant. What it means is, so I have a field, right? So suppose I take its algebraic closure, I take its Galva field, and I take any element in here, right? Drop, thanks for that. Okay, yeah, no worries. I should be done in few minutes. Oh. So if I start with any automorphism of k bar, okay, and I act this, so En of p comma q, it's a root of unity, right? And I can act sigma by it. It will be another root of unity. This is same as doing En on sigma p and sigma q. And there are some observation involved here, which I'll just say why everything makes sense. So basically, my elliptic curve is defined over base field k, right? So any, if p is a point of order n, sigma p will also be a point of order n because my coefficients are not getting changed, right? And sigma of n times p is n times sigma of p. So yeah, so those are some things I'm assuming here. So all these make sense, and they are compatible in this way. Fifth is compatibility among ENs. So what it means is, suppose I started with, so suppose, so if I start with a point that is n times n prime torsion, right? And I take a point that is simply n torsion. And n prime is like, basically I want any multiple of n, so n prime is. And I can also think of p as sitting inside this n times n prime, right? Because if I add it n times and I'm already getting 0, I can add it any multiple of times and I'll still get 0, right? So I can think of p as sitting inside this. So I can take this pairing on n times n prime of s comma p. And there should be some connection with e of n, right? Because they are multiples after all. And this turns out to be true. So the connection is, this pairing is same as doing pairing on n prime times s. So so n times n prime of s is 0, right? So n prime of s is n torsion. So n times that is 0. And p. So they are compatible in this way. Like, yeah. And yeah, I think these are all important properties at least. So I wanted to prove them, but I don't think I have enough time. I think I'll overshot it by at least half an hour, which I don't want to do. So we'll continue from here. So next time, what we'll do is see a proof of these properties. And then I'll try to, not try, I think I should have enough time. Proving these properties shouldn't take much time. So we'll see some explicit applications in cryptography. Explicit applications in cryptography. Like, how can we construct these functions g and everything, and what do we do with it? So that sort of a thing. So, okay, so let me end here. If there are any questions, we can chat. And also let me end recording.